One of the forces that's fairly important for us to understand is the force of friction. All right, it's present in anything that's moving, anything that's trying to slide, and it affects motion very, very impactfully. And we need to understand exactly why that is and what's causing this. Let's see here. All right, so the first thing to understand is just where friction even comes from. And the way I feel is best described is saying that it's due to this microscopic interlocking. What do I mean by that? Well, no matter what surface you imagine, there's no such thing as a perfectly smooth surface. If you have a piece of paper in front of you, run your finger along it, you'd probably describe that paper as smooth. Let me show you very quickly what loose leaf paper looks like if you magnify it about 100 times. Okay, that's the edge of a piece of loose leaf paper. And you'll notice it becomes very obvious that, yes, in fact, paper is made from trees. Okay, it's just wood pulp. You see little fibers. So despite it feeling smooth, it's actually very, very rough at the microscopic level. Now imagine you take two of these pieces of paper, put them on top of one another, and try and get them to slide across one another. I think you're starting to see here why you're going to generate some friction. All these little fibers, these little microscopic imperfections are going to kind of interlock with one another, make it difficult for those pieces of paper to slide over one another. That's where friction comes from. No such thing as a perfectly smooth surface. And as a result, you get this kind of microscopic interlocking. Here's like a very non-realistic version of it. So if you kind of magnify those two surfaces, you will see that they are not in fact smooth. And as a result of this, if you ever try and slide these two surfaces across one another, friction always acts opposite the motion of the object. So if you're sliding to the right, friction is acting to the left. If you're sliding to the left, friction is acting to the right. Friction will never assist you. It will always oppose the motion of the object. All right, we gotta get a little more technical, and we have to understand what's known as the coefficient of friction. It's basically the ratio between the frictional force the object experiences and the normal force from that surface itself. That symbol on the left is mu, mu, it's the Greek symbol mu, and it stands for the coefficient of friction. It's basically the roughness, okay? It's a number that gives you the roughness. It's generally gonna be less than 1, because it's kind of like a percentage, sort of. So if you look at the surfaces on the bottom, I just want to show you 0.8 is a coefficient that's fairly high because it's close to 1. That would be a pretty rough surface. But something that's a little bit smoother would have a coefficient of like 0.1. So as a quick indicator, if you look at the coefficient of friction from between two surfaces, you can pretty much estimate fairly quickly how easily they will slide across one another. Higher the coefficient, the rougher that material, the lower the coefficient, the smoother that material. Something like sandpaper probably has like 0.8, something like ice, probably closer to 0.1, maybe even less than 0.1, 0.05 maybe, something very slippery. All right, so how do we use all of this? Well, I'm going to show you an example in a second, but it is important to understand that we technically will always have two coefficients. One of them is called the static coefficient of friction, and the other is called the kinetic. Now you can jot these definitions down, but the way I would simplify it is to state that static friction is the friction that you must overcome to get an object moving. Think of like a couch that's been sitting in like a living room for a long time, especially if there's carpeting. If you've ever moved furniture like that, you know that there's like these indents in the carpeting. When something's at rest, those imperfections I mentioned earlier, they really have a chance to interlock with one another. So if you go to push something that's at rest, you really have to push it hard enough for these imperfections to pop out of one another and then allow these two surfaces to slide. That's what static friction is. What do I have to overcome to get this object moving? Once they do pop out, now, even though they're going to try and fall back in and interlock, that motion makes it a little bit more difficult. So you can see that image on the bottom, there's a little bit more separation. So kinetic friction is the friction we experience while something is actually in the process of sliding and moving, and it's always going to be less than static. Just like if you try and move that couch, at first it's going to be hard to get it moving, but once you get it to pop out of those grooves, once it's moving, it's a little bit easier. Okay, so static versus kinetic friction is a fairly important concept. So just think of that couch example as we start to look at some of these examples. Anyway, real quick, this is, again, what I just said. Just to show you, though, as you're moving that block that's at rest, you've got those really tight interlocking. It's kind of a little harder to get them to kind of become disjointed. But once you do and they kind of pop out, it's much easier to get that object moving. So just more visual example of my couch example. All right, more importantly, let's go through like a solved mathematical example because I find most people begin to understand once we do so. So here we go. We've got a 40 kilogram block. 250 Newton force, and I'm given the static and the kinetic coefficients of friction. You might notice that static friction, the coefficient of static friction is higher because that represents when that block is really interlocked with the ground. The 0.17 represents if I've managed to get those to pop out of one another. To solve these problems, we're going to do the same thing we always do. We are going to start with a free body diagram of the block. So we know we've got gravity acting down. The ground, which is a flat surface, applies a normal force upward. We've got a tension force because they're pulling with a string. And if I'm trying to move this to the right and there is friction, which we know because there's coefficients of friction, we know that it has to be going to the left. All right, step 2 is going to be to write your F net x and F net y equation. So I'll come over here, F net x. Well, let's see, I've got Ft going to the right, I've got Ff going to the left, and that of course has to equal max. And if I want to write my F net y, so F net y is going to be normal force going up, gravity going down, and that of course equals may. I'm going to do myself a favor here. I'm going to realize that this block, if it is moving, is only going to be moving in the horizontal plane. There is no vertical acceleration. This block is not leaving the ground or burrowing itself down, so I know that this whole term will become 0 because there is no vertical acceleration. All right, let's go ahead and let's plug in what we know. So I'm going to take those two equations and we'll try and write them down here. So I've got an F net x is going to equal, well, I've got a tension force of 250. I don't know what friction is, so I'll leave it as FF. My mass is 40, and I mean, the vertical acceleration is 0. I don't even know if this thing's moving, so I will leave that as AX. If it's not moving, it's 0, but if it is moving, it's some non-zero value. All right, we're stuck there, so just like in projectiles, if we're stuck with the X, let's go look at the Y. So my F net in the Y, let's see here, well, I've got Fn going up, I don't really know what that is. Weight is going to be mg, right? Fg is mg, so 40 times 9.81, and we know that that whole thing equals 0. So my Fn is going to be whatever 40 times 9.81 is. 40 times 9.81, 392.4. And when I carry that over to the other side, I know my normal force is 392.4 newtons. All right, well, how is that helping us? Because that doesn't give us anything for the x. Well, the connection, much like time is the connection projectiles, the coefficients are the connection in forces, because this normal force is connected to the force of friction through the coefficient. So now what I can do is I can calculate both my static and my kinetic frictions. How much force do I have to overcome to get this moving? How much force will experience if it is moving? So I will use this equation right here. Static coefficient is 0.25. My force of friction, we don't know. I'm going to put a little s for static friction. And my normal force, which I calculated over here, is 392.4. And I will do the same thing over here with the kinetic coefficient. You don't have to calculate both, but I do recommend it. Worst case scenario, you calculate a number you don't need, but you have everything at your hands for analysis. So 0.25 times 392.4. So the friction, the static friction is 98.1 newtons, and the kinetic friction is 66.71. So the first question, does this block even move? Well, let's see. I have to apply the static case, which is when it's at rest, 98.1, and I am applying 250. So we can automatically say block moves. How do we know that? Well, this block moves because the applied force or the tension force is greater than that static friction. If you want something to move, you've got to overcome this number. Follow-up question, how much friction is it experiencing? Is it 98.1? It is not. I overcame 98.1. This is when everything was interlocked. Now, since it's moving and they're not as interlocked, I'm actually experiencing my kinetic friction. So this is the friction I experience because I'm moving. This value over here is the reason I'm moving because I did apply more than that value. All right, it's a little bit tricky. It takes a little bit of practice. Let's go through another example. If you want to pause this and try and solve it for yourself, if you're up for the challenge, go for it. And you can unpause. Otherwise, I'm going to solve this exactly the same way I've solved the others. Start with a free body diagram. We've got Fg. We've got Fn. This is an applied force because someone's pushing that to the right, and therefore friction is going to resist that. We'll write our F net x and F net y equations, and we'll see exactly where everything falls for us. So I've got Fa going to the right, Ff going to the left, and that of course is m times a in the x direction. I've got normal force going up, I've got gravity going down, and that is ma in the y. I'm going to save myself a little time and recognize that it is not leaving the ground, so a lot of times the y acceleration is going to come down to 0. Okay, let's plug in what we know. Well, in the x, I'll do it side by side, F net in the x. Well, I've got a 150 Newton force going to the right. I don't know what friction is. Well, let's go ahead and make this a 10 kilogram block because I didn't give you that. So 10 kilograms, and we don't know what the acceleration is. We are stuck at the moment. Let's look at the y. Fn goes up. We know that the Fg is really the mass times 9.81. Safe to assume this is on Earth. And that, of course, is 0 in this case. So this right here is 98.1. What minus 98.1 equals 0? Well, that, of course, would be 98.1 newtons. So now I've got my normal force. Remember, the connection here is the coefficient. So I'm going to maybe slide down here, and I'm going to do the static coefficient first. So I'll say 0.37 equals the static friction over my normal force, which is 98.1. And let's look at my kinetic afterwards. So 0.24 is the kinetic friction over the normal force. And let's calculate those two values. So 98.1 times 0.37. So that's going to be 36.3 newtons. And for the kinetic friction, 23.5 newtons. So the answer to the first question, will the block move? Well, I am applying 150 newtons. The static friction is 36.3, so yes, the block will move. And the reason is that my applied force is greater than that static frictional force. I'm applying more than the maximum amount it can generate before everything slips and everything starts to go in motion. So the second part, again, first of all, it is moving, so I can get rid of this second piece. Let's calculate the acceleration. So I'm going to go ahead and use this equation now, because now I know that since it is moving, I can ignore this value, and I must use kinetic friction, because kinetic means moving. So I come over here and I write out my F net x equation, but for FF, I plug in my kinetic friction because this block is moving. The mass is 10, the acceleration is unknown. We've got 150 minus 23.5. That's going to be 126.5, which gives me 10 times the acceleration of the x. Divide both sides by 10. And you should find that this block will accelerate at 12.65 meters per second squared to the right. This will take some time. If you start to apply this method, you draw the free body diagram, you write the F net x's, you plug in what you know, you continue that process we've been looking at in class, I borderline guarantee it is only a matter of time before all of this clicks and starts to make sense for you. Good luck.